Hello, welcome to the Conversations About. So here it's a longer kind of conversation, lecture type thing, where I will talk about particular theories, particular papers, or anything else related to the science subject. And today we'll talk about theory of plate tectonics. So I have a little video about that, and while I was making it, I realized there's so much to talk about how people developed this theory, how many evidence we collected during the 100 years. I decided to make a kind of like a podcasty thing, just a conversation with showing some files, showing Google Earth, and having more like a discussion about that. So just a disclaimer in the beginning, I have a background in earth science, in particular geology, and I work with the mountains area, glaciers, climate change. I also have a background in oceanology, so I'm kind of like wider aspects of all the science, have this background. I'm trying to explain in my channel these all aspects for wider audience. So could be for students, for children, for grown-ups who doesn't have any science background but want to understand more about that. So I'm trying to use quite simple language and easy way to explain it, make it kind of more fun for you, and show other things which you can explore yourself to get familiar with these things. All right. So this kind of section will take longer time because there's so much to go through. And I just want to, again, as beginner, start with also saying that I lead my channel in 2 languages. So English is my second language. So some terms or pronunciation of particular words, my mind can confused. So I'm just apologize for that, but I'll try to make it as clear, as understandable as I can. So let's start with the beginning, plate tectonics. You're probably familiar about this theory. So it's a basic theory which we developed the last 100 years, and we are talking about the movements of the continents, that what people think about when they heard that, usually non-science community. But in the wider view, and you will see it from today's video, that it's more about all the processes on the surface of the Earth, which related to, of course, interior of the Earth, so these movements of the magma and the core, which is constantly creating energy, and it's drive the movements on the surface of the Earth, so our lithosphere, this thin layer on surface. The process we see in mountain formation, the topography of the ocean, topography of our continents, other geology, where rocks come from, formation of deposits, everything will be related to that. On the wider aspects, we see how evolution happened, so why in particular continents we have particular animals, like in Australia we have marsupials, which we don't have much anywhere else, and it's all be related to this, how the continents, exposition of the continents, how they moved. And if you watch my previous videos as well on the climate change, the glaciations, the climate on the planet as well, somehow depends or affected by where the continents are, and so on. So there's a very, very big topic to talk about. Actually, it's interesting to know that it's all started back in the day, and I'm talking about when it was like 16th, 17th century, first people suggested that the moment people start having maps of the continent, so the moment they start mapping these things, the shoreline, and we have better maps with time, the more they start thinking, that looks like edges of the continents look familiar and similar. And then we start collecting more data. People study sediments, so the rocks on the continents themselves, the fossils in these rocks, what type of animals and plants we used to be, so all the rocks below, they start collecting data, and they start looking at some of them kind of matching with the continents across the ocean. So, and before 20th century, when this theory was kind of developed and suggested, like one piece in 1915, there was several scientists before suggested this, and I'm not gonna name them. If you go to Wikipedia, you can find the names and works they published, what they suggested. But just kind of summarize, briefly speaking, before, it wasn't accepted much because we had this, well, first of all, science kind of was quite influenced by church, and people believed that even though there was a suggestion that we used to have like continents or bridges in between continents before the big flood, and then after big flood, which is described in the Bible, happened, we had this separation. So the animals were trapped in different, continents, and they evolved as a result. Otherwise, how, animals or even humans walk across the ocean? So all these type of questions want to explain like that. So firstly, we have this fact of resemblance of the coasts of the continents. In particular, you can see very clearly the Africa and South America, developed in the first theory of Alfred Wegener theory of continents matching each other like jigsaw. So he suggested that these continents used to be one mass, and it wasn't only based on just a shoreline, but also I will list the other evidence like belts of rocks which were found and they were matching. Maybe here on this map you don't see very well, but the scientists collected and they start matching the continuation of particular deposits that continue in other continents throughout the ocean. So they did this, and they realized, of course, as I say, animals cannot swim such a big distances, so there should be some mechanism how they transform from one side to the other. Similar, they find fossils of all the dinosaurs plants, which are very, very old, and they used to be living as one area. And this is the picture of this scientist. He was interestingly a meteorologist, and it's played a big fact that he's a meteorologist, but he want to propose something in the basic geology or geography science. So one of the reasons his theory and his supporters wasn't accepted for a long time, it will be as well because he's a meteorologist. Here I think this is the picture where he's somewhere in the Greenland collecting some data. He spent a lot of time field research in Greenland. So that's what they proposed. So he took this idea about Pangaea, the older, bigger one continent, where all continents we know now be kind of clumped together. And it wasn't just a Wegener idea, but it was, as I say, it was suggested before. I think in 80s there was already projected this theory about Gondwana, where the south continents were all clumped together, and the north continents as well. And so the geologists are, irrespectively to is people accepted in the wider community or not, they already worked on reconstruction of all the continent. So this Pangaea suggested to be at least 200 million years old, and after that it started breaking apart and separates first into two continents, northern Eurasia and North America, which is Laurasia, and southern continent Gondwana, where all these south continents are clumped together. And then after some time, 60 million years ago, these continents as well separates, and we can trace it through evolution of the animals, plants, and deposits. So what else we have? What else evidence we have here? So we have this just the Gondwana picture here with a very specific deposits. So these kind of traces of deposits which come in from one continent to other. And you would think if you have, for example, modern positions, so Antarctica so far from Madagascar and India and Africa, and only by putting them together you can, like a jigsaw puzzle, can match those deposits tracing from one area to other. And you can see we have fossils of these mesosaurs, which are very old. So we have fossils of Cynoctadus, I don't know if I correctly pronounce this name, as well, that come in through South America, Africa. We have these fossils of old fern, Glossopteris, which is quite famous for this proving this theory. And you have this other of Lystrosaurus fossils as well. But it wasn't only related to, just see what I have. Yeah, it wasn't only related to the just deposits. The geologists start seeing relation to particular deposits of volcanic rocks. Kind of we call them igneous basins, huge igneous provinces, if you would like to call them like that. So they are as well matching together, and in the past there was like one area where the eruption happened, And when we, this is the modern map, and if we put it all together back into the Pangaea or stages of Gondwana, you can trace them matching each other. So these plateau lavas in South America, for example, South Africa and Antarctica, they are of same properties, which mean they have same source, and they spread for big areas. And there was another puzzle for geologists, how we can find it everywhere. And even, if you even match direction of the way they spread, and this only makes sense when you put together these continents into our, Pangaea, into this continent, yeah? So there was another kind of solid evidence, geology, terrains, scientists that found and supporting that theory. Nevertheless, there was a big resistance of this theory, big resistance from people who can trying to explain the mechanism, how it happened. So, as I said, there was very much understanding that all continents are very stable and everything on the crust of the Earth is very stable and it doesn't move. The only thing it might move is if the Earth will be expanding. And there was actually some people who suggested, yes, our planet is expanding and the spaces between continents start growing. So before we had all continents just a solid continent plates together, and then it's cracked and start expanding and the oceans fill those spaces in between. There was a group of people who suggest, believe it might be true, but then, you need to have so much material which coming from nowhere to expand the Earth, and there was no as well mechanism to explain that. And eventually, by the middle 20th century, it was discarded, this theory, as nonsense. It's not true, it didn't happen. One more evidence I wanted to talk about, it's the glacier deposits as well. We have some older glacier deposits, for example, around the Gondwana old continent, which kind of I think they were coming from the Antarctica and they spread all around. And as well, the deposits, glacier deposits, is a particular type of material. We call it diamecton, kind of finer sand or silts mixed with coarser gravels or boulders. And these particular deposits dated, and they all same age, and they all kind of spread from the one source. And you can even trace the rims where they used to be, and then the continent spread around, and these deposits preserved in places, and we can trace it back. So there was another big puzzle. Okay, when there was one continent, we have this. It's actually happened during the Pangaea. We have this glaciation. How come we have these old deposits coming from one source? So you see the deposits, evidence of fossils. We have these terrains of lavas, plateau lavas, terrains of basalt which preserved. We have the glacial deposits. We have the interesting that the shores are matching. So all these indicating that used to be these continents being together. So the scientists, even before we have a big disprovement by other community, they even reconstructed. So this is not a very good image here, but you can see that they reconstruct. So we had Pangaea first created, and it's 250 million years ago, and then we have it started kind of crushing into two pieces first. And we created Laurasia and Gondwana, on Gondwana land, some scientists call it. And this is about 200 million years ago. And then only 140, we have a little more disconnection between continents. But you see South America and Africa, these more clearer cases of the shoreline will stay there for very last moment. And only 65 million years ago, the Atlantic Ocean started formed. And the continent separates and drifted to the modern days. But if you actually noticing the Indostan, the India plate, it was long time close to Antarctica, and it's traveled quite fast, one of the fastest movement we can notice in here, and it's moved and it's crushed into the Asia. And I'll talk about this later. And it's formed these huge mountains, the biggest mountains, Tibet Plateau, and the biggest mountain on our Earth. So that's what was in the mind of geologists, but in the same time, in 1926, there was a big conference in New York where these people suggested, okay, we have all this evidence, we reconstructed it all nicely, but there was also geophysicists. Geophysicists, it's people who study physics and mechanisms of the Earth, so they study They measure all the waves, all radiation, all the gravity properties of the earth and rocks, and they're trying to understand how it's actually working based on geology and based on physics. So it's kind of between discipline science they're developing that time, and they say, okay, it sounds great, and it will be very good if it was true, but we don't have mechanism. So it's absolutely ridiculous how such a big piece of land separates and moves so far. Like, look on the Industan, it's just moved, half of the Earth, radius of the Earth, all the way through Indian Ocean into the Asia. How come we don't have any explanation how it's happening? So it was kind of discarded, and they say, okay, mathematicians and geophysicists say, give us more evidence. We can't. It's just not feasible for us that it's true. At the same time, as I say, the geologists keep on working, keep on collecting data, and we know that that time, beginning of 20th century, times of the First War, we have so much new data collected because of the war times. They spark science as well. So there's a lot of equipment and technology has been developed for the war, and at the same time, scientists use it as an opportunity, and they use it for mapping and collecting more data around the world. And it's not just in geology, it's happened all over the oceanology. We know thrive in 50s, 60s because of after the Second War and so on. So this time the science was very globalized, already started being globalized. We have time when we discovered all pieces of our Earth, we mapped everything, so we can nicely start working on collecting our puzzle and figure out what's actually happened on our Earth. So the next stage happened after that, and it was kind of like turning point for this theory. It was in 1931. This English researcher Holmes was a scientist. He was working in Durham for a long time and then Edinburgh University, and he was the one who started proposing mechanisms how this actually happens. He was fascinated about this theory. He actually was one who involved in dating of the rocks in geology, so he was called the father of the dating in geology, geochronology, and he said, okay, we have this understanding that our kind of continents and plates, they're moving on the magma. It's kind of semi-molten material. So we already knew some because seismology started at that time, and I think it was 1917 when the first scientists discovered that we have the core within the Earth, so I have a video about that, and we have this molten mantle magma between the core and the surface. And he started proposing this theory of drifting continents. So they're kind of drifting like, ice cubes on top of the water. So the continents, they're lighter than the half-molten magma, whereas the more kind of metals and stuff. So its magma is hotter and more viscous and more dense, and the continents cooled, particular lighter materials on the surface. They're lighter and they're kind of drifting like ice cubes on the surface from side to side. He's also explained it by looking on this picture. This is this mantle, and talk about the core inside. And he suggested that we have these processes of the radiation happening here, and it's warming up in places this mantle, and when it's become warm up, it's become rising up because of the temperature. Of course, we know if we warming up soup, the hotter things on the bottom, they're rising up higher. And why they're doing this, they start mixing the rest of the medium, and the cooler materials become going on surface, they're cooling down, they become denser, and they're going down, sunk back again. So that's how you have this constant movement of the material throughout. And he suggested that we have this movement, and somehow this movement will cause movements of the crushed bits of the lithosphere on the surface. But he didn't have very specific data to support this idea. And again, our favorite geophysicists and mathematicians, they say, no, it still doesn't work for us because we need too much. They calculated how much energy you need for this, and it doesn't sound feasible to move huge continents. So nevertheless, this wider community still didn't have particular mechanism how it's happened. We have 50s, 60s approaching with very severe study of the ocean basin. So basically throughout the 50s, 60s, all the ocean basin topography was mapped and studied very well, which never happened before, of course. As you understand, before Second War finished, mostly all of the continents mapping happened. We know topography, we know where the mountains, where the rivers, all around the continents. We know the position, but we have this about 75% of the surface of the Earth unknown because it's covered with the ocean. So scientists decided, okay, it's time to study the ocean basin, and luckily, since the Second War, because in the Second War there was a lot of submarine action happening, people get tools to scan the bottom of the ocean to trace the submarine positions. So they start using this to map the topography of the ocean basin. So there was one advantage of technology developed during the Second War. So scientists just went there and they start mapping all the ocean, and we start having interesting features appearing on the bottom of the ocean. So it appears to us as on the surface we have similar mimicking topography on the ocean, but just kind of in reverse. If you look on this elevation histogram, which we usually call in geology stratigraphic curve, this is the sum of all surface topography of our Earth. So our Earth is like a ball, and if you take all the square meters of, for example, the highest mountain, the mountains from 8,000 to 6,000, the mountains from 6,000 to 4,000. So for example, we have 0.5% of these elevations on all the surface. 3% of this, 30% of from 2000 to sea level. I'm just saying approximately, I don't have data here right now. So we calculated all of them for all of the surface, and we added this ocean. This what was missing. And people found that it's kind of basically, so this is our shelf of the continents, and then you have this deeper ocean and plateaus. Most of the basins of the oceans are here, and then you have this interesting deep trenches, which as well you can find. So we have this, for example, this just a bit for Atlantica. So you see the deeper trenches here. I don't know if you can see here. Yep, the deeper trenches. So you have this general elevation. You have shelves, continental shelves. So it's all mapped. And what the first thing people start noticing, we start having these kind of mountain ridges appearing all over the ocean. Yes, so we have them kind of tracing throughout all over the oceans, and they're kind of all around Antarctica. You have them going through very classical through the middle of the Atlantic, and we have areas where they have quite a lot of them in Pacific, and even big mountain ranges coming through here. And they called mid-oceanic ridges, obviously for the position and where they are. And when we mapped it through our topography, we found it. So we have this mimic of topography on the continents and in the ocean. Another thing that was noticing about these mid-oceanic ridges, they're coming through the middle of the ocean, and that they're related to volcanism. So if, as you know, we have volcanism on the continents, and similar here, we have these huge areas of a lot of volcanic activity related to this middle oceanic ridges. And the very interesting topography, the quite rift in the middle, which spreads, and you have this crag going parallel to them, tiers, and you have volcanism related to that. And one of the famous, of course, which sits on top of this mid-oceanic ridge, it will be the Iceland, a very well-known case, and we know it's one of the places where people know for a long time, and we know it's absolutely a volcanic produced piece of land, and it's basically what we see there on the bottom of the ocean, but bring to the surface, reflected to the surface. You also have some other islands related to the mid-oceanic ridges, for example, like Tristan da Cunha Islands. So the scientists start picking up those things, and they understand that this is the rift system, the rift valley system, this, for example, mid-Atlantic ridge, which related to volcanism. And then we find the very important features, as I said, trenches. The trenches, this deep, thin line coming in the places, as we know now, related to contacts between different plates. But at that time, I don't think there was a picture yet finally reconstructed, so that we just know we have those things. And we have these kind of bigger plateaus, areas in between, yeah? So it's straight away strike the idea that we must have some kind of mechanism related to this. So this is your missing piece of the puzzle to prove the theory of plate tectonics if it's true. Yeah, this is just a picture of all around mid-oceanic ridges. We have all this lava coming out and a lot of smoke coming out, but it's under the water, so it's happening, but we just don't see it. And a lot of life, of course, around that area. It's warmer temperature. There's a lot of minerals coming out, so there's a lot of life striving along these areas. And this is the picture of the Iceland, so I just want to show you example. So these mid-oceanic ridges on the continents, we have them in some places as well, and this good example in Iceland. So we have these volcanic areas where the volcanoes erupted, and we have these places, it literally looks like the Earth coming apart. Places, we call them rift zones. And we know there's some others around the planet, for example, Baikal in Siberia, Baikal Lake. It's actually this one of those rift zones which cracking and separates, and now filled with water, which is obvious. And another famous place, it's of course Eastern Africa, another rift zone when the continent's just cracking apart. So, but on the bottom of the ocean, they are mid-oceanic ridges. And that's how it looks like in Iceland. So that's the picture which kind of summarizes what this was found just from mapping the topography of the ocean. This is already adapted for all the theory at the end, but you can see, so we have those oceanic spreading ridges, we have places where the trenches, we have volcanism on the continents, in the ocean, and we also have we call them hotspots. For example, famous is Hawaii, where the volcanoes just happen in the middle of the ocean, which we think not related to anything, but it's actually related to these hotspots in the magma, in the asthenosphere. So we will all look at that closer. At the same time, so another point we should talk about at the time, it's the magnetism or magnetic field of the Earth. So we have the spike of the research and understanding of magnetism of the Earth at that time. So here's just an artistic representation of the Earth as a big magnet, which is, we know scientists proved it's happening now. So we have North Pole, North geographical pole of this big magnet. We have South Pole, which is geographically south, and we have these lines of the meridians of the energy, which are a compass arrow align along when we're trying to measure our north position. This is just the sun here showing that it's affecting the magnetic field of our Earth. And always the side which is kind of closer to the sun, always blown by the energy coming from the sun. But actually, in fact, the magnetic field of the Earth, that's the thing that protects us from all the radiation coming from the sun. So it's very important for our life. So life probably won't be existing on our planet if we didn't have our nice magnetic field all around. So it's have a lot of implication. But in terms of our continental drift, how magnetism help us to understand that it's true or not. So people start collecting a lot of data all around the Earth at that time, as I said, and in particular people start noticing that basaltic rocks or any rocks, terrains, volcanic rocks, igneous, we call it igneous rocks that come from inside of the Earth, which have a lot of metals, in particular iron particles, iron metals. They can record the magnetic field of the Earth on the moment when they were cooling down. So if you have, the asthenosphere, the layer of the magma within the Earth, and it's quite hot and molten, and if it's above, there's a critical temperature, it's about 580 Celsius degrees, these particles of iron, they'll be just randomly, going all directions, yeah? So they will not show you the polarity. But the moment you start cooling them down, so when it's reach 580 Celsius degrees and below, doesn't matter they're molten or cooled, they start a line parallel to your magnetic field at that time. So if you take big deposition of, for example, volcanic rock, drill through and start looking through sequences is just the layers that collect in time by time, so the older will be deeper, the younger on the top, and you start seeing that this polarity would be changes. So people start collecting this and they see the recorded polarity, and we know that polarity north pole is north pole of the magnetic field, south is south, and then we start seeing this mismatch throughout the time. And all over the Earth, we have kind of pattern that developed. So in North America, for example, Europe, you have same polarity of the rocks deposited during last 60-50 million years. But if you looked in older times, they go in different directions. So the two things come out from these studies. First, we find out that our north pole of the Earth is constantly flipping. So magnetic, physical North Pole is where Arctic now, it's always there, we know that, but the magnetic field is flipping. Periodicity, it's about several million years, or could be more frequent, depends what's happening. And I'm not going to talk about why this is happening, so it's related to it's a different whole talk. It's related to the core of the Earth, and it's the way it works with the mantle and so on. But it flips from time to time. So geographical North Pole now, right now we have it, and we call it normal polarity. So it's north is physical and geographical and magnetic matching. And then when it's reversed, for example, several million years ago, it's been reversed, we call it reversed polarity. And you can see it in the rocks, very specifically in iron-bearing rocks, which cool down temperature 580 degrees or below. It's all recorded. So scientists, okay, so what we start doing? We start collecting the data from all over the world. And when they did this, first of all, yes, it's proof that we have this reversion of the polarity, but in the same time, we have this thing that two continents, and here you can see, for example, that's example of North America, two land masses, and Europe. And 50 million years ago, they have same polarity, but then with time, it's changed, yeah? And continent A and continent B, it doesn't specify, I think it was North America and Europe. And through the time, we can see they had matching, these differences in polarities, matching. And then at some point, they split. And this split, which you can see happened here 150 million years ago, this is the time when, for example, Europe should start moving to different direction. And of course, the rocks, the way they align towards the north would change. When in North America, for example, it went in that direction, yeah. So if this continent stay in the same position, like here they used to be in Laurasia, they were moving in the same curve. So scientists start doing this. Geologists start collecting this data, and they start tracing back what's happening with time with the continents. And it was absolutely solid evidence that continents actually drifted. But still, there was no explanation how actually they drifted. So we have all this evidence, but we don't have this mechanism how it actually happened. And even when this polarity drifted as well, we're talking about this polarity flipped because it's very important for next point. It still was recorded, in this. So when you already assume the flip of the polarity, you assume the geographical north position, and modern days you put these two lines and they should match each other. But if you assume and you know how the continents moved, for example, and you will calculate it into this graph, it will match eventually the normal polarity, the polarity of the rest of the continents. So this is all fascinating, and it was fantastic evidence that yes, continents moved physically, respectively, to North and South Pole. So the turning point for all this theory became in 1963, where two researchers, Vine and Matthews, they were part of the researching the bottom of the ocean, in particular these mid-oceanic ridges. So they had some studies they did on northern part of mid-oceanic ridges in Atlantica, so basically a little bit just southwest of Iceland. So they start recording not just topography, they also start recording the magnetic polarity of these deposits. And at the same time, they were collecting the ages. So they collected samples actually from the bottom. So if this is our recorded area, and they collect samples of how magnetic charged this area, how thick this deposit, and what the age of it. And they will continue outwards from these mid-oceanic ridges, start collecting their data. So they start studying all the basin, and they start having these absolutely beautiful maps of very mirroring each other collection from both sides of the ridges. So I think on this next picture you can see it much nicer. And the thicknesses were very matching each other, basically mirroring each other. The polarity was matching each other as well. So this magnetic polarity, reverse and normal, reverse and normal. Yeah, it's actually here normal magnetic polarity. That's what I found. And then they have reverse. Then they have normal, then they have reverse, normal, reverse. And you see the thickness and the distance from the mid-ridge is absolutely identical. And surprisingly, they also collect the dates, how old these rocks as well. And progressively, the more you go further from the middle, they become older and older. So as a result, they get this picture, older, same polarity rocks. So obviously they were deposited at the same time, they're younger, same thickness, younger, and you can see how the polarity changed. And it's actually, it's I don't know if it's true or not. There was like a legend that one of these researcher, they creating these maps on a big sheets of paper, and one of them he was taking home, and he kind of just put them, folded it together, and that's how he saw when he folded it in the middle the identical matching mirroring of these layers. So he come out with this idea that that's the source where the rock's coming from, and the moment they erupted, coming out on the surface, they're cooling down, they've been representing the polarity of that area at the time, of the planet of the time, and then new rocks come in next time, and they're pushing these older rocks to the sides. So this is the picture when you can see it, polarities as well, and how progressively we move. So stage 1, deposit there, then come next time of deposition, and next time of the magma coming to the surface, pushing them to the sides. The fantastic idea, and as a result, that's how we can kind of reconstruct it. Mid-oceanic ridge, we have this new magma constantly supply, and it's pushing the rocks to the sides. And you have, these black smokers related to the volcanism, of course, and as I said, like Iceland and other islands related to mid-oceanic ridges. And whatever you have on the surface, and we know the continents, they much lighter than oceanic crust, because oceanic crust much denser and thinner, and I don't know if I have a picture, yeah, and the continents they made for thicker and lighter materials, like more silicates, calcium and other type of materials. So they float on top of the oceanic crust. And all of that, so for example, this one big plate we have here, African plate, she's all bouncing on top of the asthenosphere, which is high layers of magma. So when they see this and propose it, so they did some measurements here, as I say, south of Iceland, and everybody starts straight away pick up this idea and start measurements all over the ocean. So in several years throughout, people collected all data from all over the ocean, and they find exactly the same pattern everywhere. You can see a little bit mess in Pacific Ocean because we have a lot of these ridges, but they keep spreading, and it's all matching. And here, this is the ages of the ocean basin. So we can see the oldest basin of the ocean we can find around Mediterranean, which is 280 million years old. And the youngest, it's obviously will be related to the mid-oceanic ridges. And then you go older. So basically in the big oceans, we have the oldest gonna go up to 160, 180 million years, but not older. The only little bits preserved, it's in the Mediterranean. But what's happening, so we know that planet is obviously older than 280 million years. We have rocks on the continents which much older. Piece of ocean crust will be going somewhere. So it's not just disappearing. So it will be going somewhere, get recycled. And that's when people start looking into these trenches as well. So, and we're noticing where we have these trenches, that's where this ocean crust get consumed, absorbed or dissolved or eaten away, melted away. And that's when the people start, when we have those all idea, we created, you see these maps of the plates. And the result, coming back to this image, we can recreate these areas which have been found as a result of these studies. So you have all this evidence with the continents, which we talked about at the beginning. We have now solid evidence on the bottom of the ocean with spreading areas. We have places where our crust get disappearing, consumed by the continents. And we have volcanism and trenches formation related to that. We also have places where actually, as I said, similar like under the water, but on the surface, on the continents, we have spreading as well happening. So particular, 2 rift zones west of Africa and Siberia. There's some areas around North America on the west coast. So we have those areas as well. We have places where produce new crust, consume it. And there's also places where the 2 crusts coming towards each other, 2 plates coming towards each other, and they just keep kind of pushing towards each other. And if you push 2 pieces of rubber towards each other, it will go somewhere and it will become thicker as a result, and kind of gonna slide against each other and produce maybe mountains and maybe the faults. And in geology, we have absolute relation to fault systems to these plates, and they developed. We have big faults developed in the areas where 2 continents kind of crushed and smashed towards each other. And very famous ones, of course, San Andreas Fault, North America. It's kind of strip slide fault. We have fault famous in New Zealand, South Island. We have faults all around the planet. We can see them. After this all was collected, all this evidence in 1980s, this theory was accepted widely now, and it was all supported, it was all approved, and the bigger picture arose from that. So basically the modern geology, the modern understanding of plates, volcanism, rift zones, trenches, it was all supported and developed since then. And in 1980, where even geophysicists now understand how actually what a asthenosphere or magma play a role in it and how the mechanism works, it's become all acceptable. And the more we looking at the surface of the Earth and the ocean, the more we collect evidence. At the same time, this theory helped to understand many other processes. For example, I thought about this Hawaiian Islands, and there was one thing that was found that the Hawaiian Islands. So the Hawaiian Islands, where are they? They're kind of not. They're in the middle of the plate, yeah. So they're not related to zone of contact. So we have this Marianic Trench. We have the deepest trench here. We have all other trenches related to the zones where the continent, the plates meet each other. So, for example, that's what I was talking about. We have 2 plates, Australian and Pacific, crashing towards each other. Huge trench formed in the ocean, and then we have New Zealand, which it's on the border between 2 plates, and that's why New Zealand is so famous for our earthquakes and volcanoes. So North Island, it's basically, you see, it's coming almost here in the middle, and it's all volcano plateau, the famous Topa, the big plateau here. All these volcanoes are formed here, and then we're coming through the Southern Alps of South Island, and you can see how it's this trench kind of coming through the land, curved, and continues further down towards Antarctica. And that's why we have this fault. You see this line, it's very obvious on a satellite image. You have high mountains to the east, which we call Southern Alps, with the glaciers and ice, and we have this nice straight line coming through the west coast. You can see it very well. So this is your fault. Of course, it's a little bit developing for other subsidiary. There's many other subsidiary fault, and one of them is that actually coming through the Christchurch, which erupted. in 2010 and 11. But we have all this fold, big gigantic float, when with this plate, Australian, is kind of moving a little bit east and north, and you have this plate moving a little bit west and south. And even when you start matching the valleys, all the valleys where the glaciers used to flow, they all moved to the river valleys and all the glacier valleys. So we have all this evidence all around the plate. Well, similar North America. Yeah, this is another area, rift zone, as I want to show you the separation of the plate, and this is the birth of the new ocean. So in several millions years ago, it will be exactly what's happened between South America and Africa, and this will start moving apart in the rift zone, and will start creation of new ocean and separating continents. So what happened here? Yeah, you see, so this is in the big picture. Similar in Africa, you have this absolutely amazing rift zone coming through all the way the west, and I think this little bit continue here. So this is the new ocean as well. So this bit will move in there, this bit there, or somewhere like that in particular. So let's have a look. North America as well. We have the Sunrise famous fault, which all the system of the biggest cities in the world sitting on and in constant danger, similar like we have it in New Zealand. And we have also the rift zone is happening here, and you have these trenches. So there's a lot of activity going on, and you have this big trench here, 2 plates as well, and that's where we have a lot of big Denali fault and a lot of earthquake happening in North America. So it's the more we start to understand how the crust work, the ocean, the more we have evidence in geology, the more we understand formation of the rock. And basically most of the geology, geography, landscape, oceanology, everything we know now, all the science based on this fact that we have these plates, and in places they coming together, crushing, in places they separate and goes apart. So let's come back to Hawaii. I didn't finish talking about that. So Hawaii, there was the little puzzle. It's in the middle of the plate. So if we look on our image of the plates, the hotspot, it's a little area where asthenosphere kind of coming closer to the surface, more hotter material coming towards the surface. So, and it won't be related to this as we seen before convection zone, when there's just a constant bringing of hotter, lighter material up to its surface, cooling down and moving back. Yeah, so this mixture. It will be just kind of odd places where we have something going on, and a little area will be affected. But they found to stay for a long time. And as we talked before, the plates are moving. So you have these movements, and it's been recorded now with GPS, global position system all around the world. We know we know everywhere what the speed which the continents and ocean is moving with. So in an average about 2.5 centimeter a year we have movement. So, and of course, it's constantly moving. For example, this plate, if it was our Pacific, it's moving towards Eurasia, and you have this Hawaii island formed. But then what's happening, the hotspot stays in molten underneath material, so it stays in the same place, but the plate keep moving. Yeah, so this island will be shifting, and then it'll be going off. Like for example here, it will go off this hotspot, so it will volcanic activity will stop to cool down and stop, being eroded or occupied by corals, animals, humans, or so on. But the fresher kind of lithosphere, oceanic crust, will come to this hotspot, and the new volcano will be developed. And depends how active hotspot, bigger volcanoes, bigger islands you have. So let's come back to our Google Earth image. Yes, that's where this area, and you can trace this hotspot coming all the way through these islands. You can see there's older, more eroded, kind of more atoll type of islands preserved. And then the more we come into the modern one, more younger one, it's more active. There's one of the biggest volcanoes. We know active, biggest volcano we know right now in Hawaii. So please go there and visit. And you can see this, the older islands cooling down. So the hot spot used to be, it's always been kind of here. if you think about, under the crust, but the plate is moved. So you can see, and it's nicely matching with the direction and the rates of movements of the plate and the dates of the activity of these volcanoes, rock formation. So it's very well studied. It's a fantastic example and representation of what we talked about. So another little evidence in our box for how the plate tectonics happens. So that's basically how the last 40 years the main plate tectonics theory established, and majority of geology you now understand, now you study, you read about. Majority of the papers that published in international research journals, magazines, most of them will be following the plate tectonics. And here I show, this is the Mangkok, the highest mountain of Southern Alps of New Zealand. This is the Southern Alps. You can see the range coming through. In the west we have Australia plates crashing towards Pacific plate. So majority of the mountains, as I showed you before on Google Earth, they are sitting on the eastern side, so on Pacific plate. So this is all material that used to be bottom of the ocean, accumulated sediments accumulated bottom of the ocean, and then when the Pacific moved towards the Australian plate, progressively it starts kind of rising up from the bottom, scraping one on top of each other, folding these rocks. And when they meet with Australia plates, we have fault, as I show you, developed. So the fault going just to west of here, not far, and these rocks just keep moving, keep pushing towards this Australian plate. And if you ever seen the maps of being on South Island of New Zealand, there's a highway going west side of these ranges, just west from here, where it's quite a flat area with a series of valleys, and you have the mountains on the east. I'm just explaining you this about New Zealand because that's my main field site. So I photographed it from this picture from south, looking on the Mangkok, the Hound Mountains, and it's very nicely represent how this collision of the plates happening and how it's important for us to understand processes on the Earth. So if we didn't have this plate tectonic theory, understanding, all this formation of the rocks, trenches, faults, it will be all kind of, strange for us and random, yeah? So another thing, that's the picture. So I'll show in that area Alpine fault coming through. This picture showing all these zones, and in particular you can notice you heard about a rim of fire. So that's the number of volcanoes and earthquake which going all around Pacific, Antarctic plates all around, and this is one of the main zone we know right now where the most earthquake happened and volcanic eruption. One of them is coming through directly through New Zealand. This just an image of volcano of White Island, which actually recently erupted and several people died last year. Just a volcano on this collision between Pacific from the east and Atlantic plate from Australian plate from the west, and the volcano erupted, and it's erupted up. So it's quite high area here, so the volcano reached the surface. If it was underwater, there will be underwater volcano. And the last thing I want to show, it's talk about, so these zones we talked about between plates. So the first zone will be where we're spreading the crust. So in the middle of the oceans, mid-oceanic ridges, we have rift zones on the plates. Continental plates, which is Eastern Africa or somewhere in North America and in Siberia, and we have places where these plates will crash towards each other. And Rim of Fire, it's the famous zone where subduction happens, so the oceanic crust going under the continental or two ocean crust meet each other. And in India and Asia, plates when they crushed, so Indostan plate and Eurasia plates crushed, we have the most famous mountains formed, Tibetan plateau. So all the Kathmandu, the highest mountains of the world, are located here. And this picture beautifully depicts this, how it's happened during the last 60 million years. So India very intensively, very fast moved towards Asia part of Eurasia plate, and it's crushed, and you can see how these layers, the plateau and the mountains, they formed by kind of scraping material, the Asian material and Indian material toward each other and building. And when you do this, there's some material going down, some material going up, so you have thickening of the crust, and as a result we have the thickest mountains formed, and they very active, they keep rising up, the highest mountain on the planet. You can see it's happened very fast, so that's why we have such a big mountains. It's the biggest mountains right now on the planet. If you calculate the rates of, if the movement was slower and the erosion was quite high, the mountains will probably maybe doesn't grow as high. So it's all about the ratio, how fast you produce, the thickness, and how fast erosion destroy the mountains. Erosion during the collapse, like landslides, rock falls, weathering, and so on. See my previous video, I explained a little bit about how the mountains and rocks erode and collapse. So if the Indian plate was moving quite slowly, it will be, and it was eroding same rate, we probably didn't build such high mountains. But because it's moving very fast and there's not enough erosion to kind of destroy them, the wash them off, so the mountains keep building up. And you can see this how they calculated that the plate, the material was melted in, and then just a bit by bit they will start moving down, that this more denser material will sunk down and get recycled into the mantle again. And there's conversations about roots developed, so the higher mountains you have, the bigger roots you will have underneath. But it will all worked on kind of beyond like ice in the water, that's how the continent actually floating on the mantle. And it's just another graph representing the same history of formation of our Tibet plateau. So that's basically all I want to talk about theory of plate tectonics. It's very interesting. I found in the last 100 years developed. We have evidence collecting steady throughout several decades. And it's fantastic how between disciplines we have all these new discoveries happening, like especially after the Second War we have a lot of new equipment, new technologies developed to study the ocean basin, which before wasn't so available for us. And it's all playing role in establishing and understanding the plate tectonics. And I can tell you that majority of studies at universities, textbooks, science right now based on it, formation of the mountains, I say oceans, volcanoes, and so on, faults. But there's also scientists who still maybe think about that it's not true, so that the continents are immobile, so they stay where they are, and they just explain formation of the oceans different way, and they just explain the formation of the mountains different way, and volcanoes as well. And I really respect the people who kind of very open-minded. They're trying to find different ways to explain something what we traditionally explain. Now plate tectonics is kind of to be traditional for us, but other scientists have different ideas. And I can tell you from my personal experience, I had a professor, head of school. You can imagine, head of school, so it's very much a lot depends on his ideas. He had his theory of formation of the oceans and continents and mountains, and it wasn't about plate tectonics. So when I was doing my exams, I had to memorize his books and his evidence and his theory, and I have to know also very well the plate tectonics and traditional view. So when I was going to pass my exam, it depends which teacher I'm going to. It was exams when you have to go and talk to the teacher. It wasn't written exams. So if I go to the professor who is plate tectonics one, traditional, I just have to talk about that. If I get my professor who's head of school and believe in different theory, his own theory, I have to spoke about geology from his point of view. So I can tell you, and there's still people who, I don't know if they publish much papers because it's hard to be peer reviewer and come through the reviewing process, but there's people still have their own theories developed. And I really encourage people to look in different science areas as well. So there's many people who right now very specialized in their field of area, but they might not know so much or enough about other aspects. For example, if you're a geologist, you could be very specialized on volcanoes, and you have very poor understanding of other aspects of geology or climatology or geography. And in my, if you had this knowledge of other aspects of earth science, you might have bigger, greater ideas. And on the example of plate tectonics theory, we see how all these physicists, geophysicists, oceanology, everything come together to support the idea, and physics, understanding the magnetic fields of the Earth and understanding fossils. So it seems like in modern days, be very specialized to know your area very well, but it's very helpful to have this cross-science communication and understanding to see bigger picture. So that's what I'm trying to do. I'm trying to talk about earth science in very accessible ways, so people from different science or not even science areas can relate to it, or maybe see something which they can support with from engineering field of view, or chemistry, or astronomy, or something like that. So I hope you enjoyed that little talk about plate tectonics. There's so much to talk about, and if you have any questions, please comment it. I can explain you in the comments reply, or I can maybe make another video, shorter or longer one. We can talk about that. I'm planning to have more this type of conversations, maybe in terms of I can make them like a live streams as well. And I would like to not just talk about bigger problems, theories in geology, earth science, but also look at things like specific papers or recent published papers, recent published theories, which shows what's actually happening right now in Earth's community. So I will try to work on this, and please support me meanwhile. And thank you so much, and I hope you really enjoyed it, and have a lovely day.